The topic 2 weeks ago was P2P cloud systems, and we had an overview on first how to monitor peer-specific information. So how can we find peers with given characteristics, for example, CPU use, CPU power, or storage space, or online time, or any kind of peer-specific information in a large network. For that, we had a look at tree-based systems and how this can be done so that we still can access all of the information quite quickly, but none of the peers storing the information is overloaded. So that's what we did last time. And what we were aiming at, and what's basically the next step towards peer-to-peer based cloud systems, is to first have a vision. And the vision was, let's assume we have this network of several users and all of them have some resources to contribute. This may go up to millions of users, and you all have some free storage space or CPU power at your PCs, and that you are willing to contribute. And what you would like to do is to somehow make it available, but using a simple approach is somehow problematic. So if you would have only one-to-one mapping, then we have the problem that peers are going offline quite quickly. So an average online time of a peer is typically 4 hours, and if you want to host your data for a longer time or do some longer calculations, you need some more advanced techniques that do not just assign you to one of the other nodes who has that capacities, but also make sure that you have this reliable reservations for a longer time. So that was a problem. So there are also measurements how long the nodes are online. So here, for example, you see a probability that the node is going offline on the y-axis, and on the x-axis the online time of the node. So if the node was already 800 minutes online, then the probability that it will fail in the next 50 minutes is around 10%, and that it will fail in the next 10 minutes is quite low. So this is the lower curve. So there are measurements just showing that peers are very frequently going offline, and it's quite tricky to really, if you want to have long-term living services running on those peer-to-peer networks, then you simple one-to-one matching, it doesn't fit. So we will see how still with peer-to-peer mechanisms, reliable reservation could be achieved. So just to see what kind of components might exist and how you could combine already existing solutions to create a scenario, to create an application where you can really host a service, or to run an application for example 2 months, although every peer is leaving after 4 hours. So to show you just a big snapshot of how you could combine this kind of peer-to-peer application. So at the top, there you have the structured peer-to-peer overlay. Then you have some monitoring for the capacities. Then you can put on top of it another layer, which is helping you to manage these resource reservations, for example. And what it does, to give you first a big picture, is that you can find individual peers which have desired qualities, and you arrange them redundantly. So you do not pick only one peer providing the resources that you want to have, but you pick several ones, and this is done in this layer. So, and then the use case and what is usable for the application or for the user side is that you have an initiator that could ask for a specific time it wants to reserve the resources, and it defines some requirements on the resources. For example, storage should be over 200 megabytes and CPU consumption less than 20%, and it receives a reservation ID. And this reservation ID can then be used to always ask who are the peers which are currently providing me this service, and also other users can ask with the same reservation ID. So not only the initiator can access those reserved resources, but also other users. And this layer on top of the monitoring of peer-specific information layer makes sure that there are always sufficient number of peers providing the resources, and although every peer has a limited lifetime, and might fail, there is still a sufficient number of peers so that the service itself, the requirement, and the reservation is always running on. So, how can you build such a solution? What are the elements? So first, you need some. You need to set up the reservation. For that, to do it distributedly, you somehow have to You have to identify first a peer. That's a DHT idea. So to have a peer responsible for that reservation, identified by an ID, and that you can somehow find out. So probably you have your reservation consists a set of resource constraints, for example, on the CPU power, on the memory, reservation time, and somehow a degree of redundancy. So how available should the service be? So here it doesn't make sense to take 100% because it's very hard to have 100%. So if you take, for example, 99% availability you aim at, then it's easier to calculate how many nodes are needed. So these are the known components. Just to present to you what kind of elements you have. So you have the peers who provide the resources. You have the tree, which enables you to find more peers which are suitable. You have I think we go anyway to the protocol. And what you want to have is you want to always have some main manager who is maintaining your reservation. So the use cases that typically, if somebody wants to host a service in a peer-to-peer cloud, you do not want to stay always online to manage it yourself, but you want somebody to make it for you. So you pick some main manager. He has some backup nodes, a management so-called, which is they are checking their liveness all the time. And this main manager is the direct access point for your request. So you initiate your reservation there, you get the providers. He's managing the resource providers. He's looking for new ones. And if he fails, then a new one is picked from the management set. So he's also not really needed. He might also fail. Okay, so now how the whole process is structured is that you have this main manager in the peer-to-peer network, which you identify by its ID directly based on your reservation. And that node is periodically checking whether there are sufficient number of nodes providing you the resources that you want. So if you defined in your requirement, okay, I would like to have a availability of 99%, then he has to make sure that the nodes that he picks are fitting to your requirements first, so with terms of memory and so these resource constraints, but also that the probability that they will fail is below 1%, for example. And how can he do this? So for that there are some common measurements on the expectancy of how long peers will stay online. So this is, for example, a graph depicting it. So if you take the periodical rounds in which you check whether the nodes are expected to stay online, for example, with 100 minutes, and you have one peer, then the probability that it will fail is 60%. However, if you have a set of 3 nodes, then the probability is only around 15 or 10%. And so you have very wild combinations, but you can calculate what the probability is of your nodes failing in the next round. And this is what the main reservation manager does. So every round, every periodically, he checks whether the current provider set is expected to fail in the next round, or how high the probability is that it will stay online. So, and this is compared to your reservation availability. So we assume the resource provider set is not empty. We check their lifetimes, calculate the round survival probability, and if the number of surviving peers is above this availability requirement, then we sleep for the next round, and if not, then we pick a new peer. And how are new peers picked? So for that you can determine first how many new peers you need. Then you find the suitable peers with an appropriate peer selection mechanism, which gives you peers based on their capacities. and you contact them and add them to the resource provider set. Okay, and just so this topic is anyway not so long. The main question was from the beginning in this peer-to-peer service, peer-to-peer cloud environment. Can a peer-to-peer system host long services, especially if every individual peer fails after a short time? And this solution, so P3R30, so peer-to-peer protocol for resource reservations, reliable resource reservations, and offering, it was tested. So the resource requirements were, for example, you wanted to have 500 megabytes of storage, that amount of upload capacity, and the reservation time was 200 days. So in total, we wanted to use these capacities for 200 days, although every individual node fails after 6 or fails after 4 hours. And the success probability should be 90%. There are two approaches basically. Yeah, here's the simulation setup, but the important ones are the average online time of every peers is around 4 hours, and the reservation time is 300 minutes. And there are basically two approaches that were compared. Either you increase the number of peers that you take, so redundant peer approach. So instead of just calculating how much peers do I need to really meet these 90% availability, I can also add 1, 2, 3, 4, 5 more peers to that set. Another one was the probabilistic buffer approach. So although we just want to have 90% availability, we still add a little bit more to minimize the risk that we miss that deadline, threshold. Okay, and it was tested with several number of nodes, up to 4,000, and out of these nodes, 5% were starting a query for this amount of storage and service resource reservations. Okay, let's see. So just as a backup slide also for the peer selection. So here you see the number of nodes. There were also some peers, some churn. So it starts with, in the beginning with 1,600 nodes, and it dropped quite quickly. And the ratio in this, the black dot is showing how much of all of these nodes is known to the root and its support peer. And it's just showing, okay, quite high frequency, high ratio between 1 and 90% of all nodes were known for the peer-specific information search. Okay, but we wanted to focus on this resource reservation, and using the protocol sketched before, it was shown that it's really working. So here in this right picture, for example, you see it was calculated how many nodes do we need to meet a 90% availability until the next round, and 2 more nodes were added, and those were reserved. And this is the plot showing the lifetime of all of the peers that were used. And as you can see, the reservation was reached. So the red one is showing the probability, the current availability probability. So it's showing the probability that the nodes will really stay online, and the green line is showing the 90% that we really want to meet. And the other one, this probabilistic buffer approach, is showing, okay, we assume we have a 90% availability that we want to reach, and we add a little bit more, so 0.93 as an availability, and that leads to a too small number of peers. So we had in this point a reservation miss, and no peer was keeping the data at that point. And if you add more redundancy, so in this case it was additional 5 nodes providing the resources, and you see there's quite much more redundancy, which is keeping the whole reservation available. On the other side, if you also start with a probability of availability of 90%, but you add a little bit more. So in this case, it was added that we took for the availability requirement 0.99, and although the reservation was met, our requirement had also the availability of 90%. So we also always wanted the probability that the peers fail is below 0, so below 10%. This is not the case here. So in this case, it was the risk there that if some more peers fail, the whole service fails. It didn't, but the risk was there. Okay, so concluding, this is just some more overview, but what what it tells us. So if we just look, for example, for this redundant peer approach, so just adding 1, 2, 3, 4, or 5 more peers, leading to a redundancy of 2 to 6. Basically, if you take a redundancy of 5 to 6, then all of your reservations are reached. That's basically the statement. And if you look at the total number of peers, how many peers are used in this long time of 200 days, then for the redundant probability approach, we have up to 70 peers that are used on this long time, and with the other approach, it's quite less, but it's also not that successful. Okay, just to say some words on the costs. I think this is also the last slide for this. So if you really want to have these reliable reservations, and we saw that with 5 to 6 nodes redundancy, you have a 100 success probability to reach it. The cost for maintaining these peer set was 2 megabytes over 200 days, so additional traffic costs. And with the other approach, it was 0.8 megabytes. So this is all negligible cost, basically. So you can provide this in a peer-to-peer fashion with not much more overhead. And the starting delay, so how long did it take to set up the first set, provider set? It was below 15 seconds. Okay, so to summarize. So we, for these reliable resource reservations and aiming at peer-to-peer cloud applications, there we really need to be able to provide this platform with reliable services, reliable resources to host any kind of applications. For that, the first step is you need this monitoring of peer-specific information, so that you can find peers with given quality criteria. And the second one is you need that reliable resource reservation. And it was shown that if you pick the right peers due to your requirements, and you do it redundantly, so with a number of higher than 5, then you have 100% success. So in the simulations, at least, it was 100% success ratio. Of course, there's a very small probability that still all of them fail, but it's very small. Okay, and next questions regarding this peer-to-peer cloud applications is what kind of services can be handled. So if you use redundancy, it's good for stateless services that can be run in parallel. But what if you have state? So if you have to coordinate these services, how to handle that, how to handle security, and also if, for example, you have a very popular service, then those 5 redundant nodes are probably overloaded after a short time. So the monitoring load should also, the load should be monitored and should also lead to more redundancy, for example. Okay, so that was the part that we were missing last week. Now I would like to jump over to another topic, which is not the next one according to the website, but it is still more important. So we'll only have 2 more topics basically in this lecture. So one of it is evaluation of peer-to-peer research that we will see now, and next week we will see a very popular, very new trend of peer-to-peer applications, which is peer-to-peer based social networks. So we will today, however, still continue with evaluating peer-to-peer research, and we will see how to do it. So, just to give you an overview, we will see, okay, what can we do with analysis? What kind of statements can we obtain by it? What kind of simulation results? What can we achieve with simulations? Where are the limits, and what are simulations for, especially in peer-to-peer environments? And what kind of prototype testing can be done, and what kind of statements it might provide us. So all of these approaches are somehow incomplete and provide only a small view on the protocols that are tested, but together, combined, they are quite powerful. Okay, so let's give you first a big picture on all evaluation approaches that we have, and then to go into the detail for every one of it. So let's begin. So we have, let's say, a peer-to-peer based algorithm, something that we find very clever. And now what we have to do next is to basically we can evaluate it in on various levels. So we can evaluate its general idea, but we can also tend to evaluate the detailed implementation, for example. So one approach to really have a big picture evaluation is analysis. What you come up with is that you describe, that you model your approach and you simplify it in a bit, but you can derive some proofs on properties on it. So for example, that's very typical in routing. So for example, you can calculate how many nodes might be reached in worst case, or in worst case, most often. So you can define performance bound and complexities. Of course, it's very general. It doesn't contain code and all that, but we will see what the benefits are and what it can be used for. So but there's no code involved. So the second part is what gives us somehow more information is simulations. So especially with peer-to-peer networks, so analysis can tell you if I have n nodes, then the complexity for lookup is this and that, O log n, for example. And with simulations, you can also you take fake code, so you simplify it a bit to have some shortcuts to make it easier to handle a large number of nodes. You have not a real network, but you also emulate it. You just assume and calculate some expected delays between the nodes, and you do not have real user motivation or user models, so you also make it up yourself. So, and you also need to optimize the code for the simulations, so you can use the shared memory of the simulator. You can monitor it more precisely, and the goal is, especially for peer-to-peer networks, is that you somehow can induce some controlled actions. So you tell, I want to evaluate 10,000 nodes. All of them should perform some specific lookup procedure, and then I want to measure what is the expected quality of service. So what are expected average lookup times? What is the variation? How is the load varying? Where performance leaks? And that you could observe. What you can also do is, if you use various scenarios to identify and to really test the performance of your algorithm under various conditions. This is quite hard to do in analysis. So just think of you would like to simulate chord in a mobile environment with slow peers, with low bandwidth in comparison to a high bandwidth environment. Then of course it takes effect on the expected lookup times, but this cannot or can very hardly be modeled. The next step, if you want to evaluate your peer-to-peer protocol, is that you really implement it. So you do not do any more shortcuts to, for example, use the shared memory to communicate between the nodes. So you take the real code, but you do not take the real internet. that has the benefits of here, for example, with simulations, you some good value, you could simulate 10,000 nodes on one machine. With real code, it's probably only 100. And in order to still handle it, manage it, you don't run it on the real internet, but you fake the network and you fake the user. So you just define some user behavior, and you test your real code. It enables you to run many instances on a few devices, but with real code, so you can really say what the properties of it are. Once you have done it, you can start an alpha test with real code, real network over the internet, but you use fake people. That means you use only a limited user base which you trust and which you can control, which you can ask to do some specific actions, to follow a protocol, to test your software, and finally a beta test where you release your whole software and your whole protocol and you test it under real conditions with real users in a very hostile environment. So it should be very secure, and but also it's the hardest, and you also get the most useful results. And we will have a look at all of this. So to give you an example, something that's more common now, so from the last lectures, so you know the tree structure of Sky.com and how it works, and the good thing is it was evaluated with various of these approaches, and it was evaluated analytically to identify how the tree structure evolves, and it was simulated, and there was also testbed evaluation, which helps us to see what are the benefits of these evaluation methods. So the focus is not on how this tree performs, but what the evaluation methods can tell us. So starting with analysis, so one approach, and assuming the tree structure in mind, what we can do is, and what is needed is a more simplified model. So all that is somehow difficult to handle, like heterogeneity, a distribution of peer capacities, various peer-to-peer delay or latency, and all this is simplified. So you assume homogeneous nodes, all of them are similar, you have a set, and you have probabilistic actions, and if you simplify these assumptions, then you can come up with some proofs and you can show some properties of the network. For example, the tree can be identified or modeled as a weighted directed acyclic graph, and for that already some theorems are known, so how it performs, and how the tree height is, and how the lookup time is, and it can tell us that kind of general results. But what are the weaknesses? It might tell you, okay, my tree height is O of log n, and every node can contact the root in that amount of time, but what are the constant in this complexities? So that's sometimes more relevant. So if I'm going to monitor the network, then I'm not just interested what the complexities are to reach the root, for example, to aggregate all the data, but I'm also interested in exactly how many seconds are needed. So if I have an update interval per node of, let's say, 10 seconds, how old is my information in the root exactly? So can I define some threshold, for example, that the information should not be older than 10 seconds overall? How are the parameters to choose? And such things are hard to handle with an analytic approach. So how is it done? So the system model, which is typically introduced, is describing the system properties and behavior, and it's getting difficult to identify the appropriate level of detail. So either you make it very easy and modelable. So for example, you say it's a tree structure where you can define height and number of nodes per level and all that, or you go into detail and pick up more and more of the protocol. characteristics. For example, how the nodes are found and how big the responsibility area of every node is, and that might make it more problematic to come up with some solutions. So typically, an analytical approach tends to be more simpler, and you will receive some more general proof. For example, if you take the tree structure, you have some statements on the tree properties, and you can define also some upper and lower bounds on how old the information in the tree is and how many nodes are affected and how much the worst case traffic on these nodes is. Yeah, here are the graphs. So for example, you can define that the gathering and dissemination time is of this complexity with the branching factor beta, number of nodes n, and update interval is how long every node is waiting until it resends its information. And then you can calculate what the average age is until what is received at the root, for example. So, and often also in this case, if you look at the graph, so it's not important what is exactly inside, just the method of analysis is important here. And typically also here, so all of the nodes are assumed to be well-minded, so they are all complying to the protocol, they are all homogeneous, they do not differ in their capacities, and also if the tree is enabled, so there's no peer-specific information that is somehow modifying the protocol. All the actions are typically probabilistic, we don't have delays, loss or time effects, and it is on one side okay to find out what are the worst case complexities, but if you really want to use your peer-to-peer protocol, then you are interested in this time effect. So you really want to know what is the aggregation time of the whole information and how much traffic is generated exactly, and what is the load difference between all the nodes. So that's what you want to know. Some more graphs. I'm not sure whether it's relevant, but it just shows you, if you plot it, then very nice curves, and it's nice to see. So you can calculate the number of I just jump over it, it's not that relevant. So the next step is that now that you know these worst case complexities, you want to find out, okay, let's make the models of the nodes more diverse. So we want to introduce peer characteristics, like every peer should have designated bandwidth, designated position in the world, and also that should correlate to the delay it creates during the communication. So you want to introduce there the specific node characteristics, capacities, behavior, different user models, and to see what happens. So what happens if 5% of my nodes are malicious and my peer capacities are according to the OECD measurements from the whole world. So you really want to use valid bandwidth models and to see whether it still behaves well and expected, or what happens. Of course, you cannot do it with unlimited number of nodes, so you have to reduce some parts. So you can probably take only 100,000 or 10,000 nodes. And you want to find out finally what are the response times, traffic and node load, and because it's still relevant whether your result is available in 1 second or 5 seconds. So if you want to have a practicable solution that is also used in reality, then you also should look for it. So what can you do there? In simulations, what you cannot do in analysis. So you can really define various user models which also react on each other. So for example, the selfish node could also change their behavior based on their observed success, for example. You could use various protocols, various workload that you define. And what you find out and what you get out is an overview on the quality of service, like response time and traffic and all that over time. So how do you proceed? So you first implement your algorithm, but you use a controlled environment. So this is typically the simulator. that helps you to to save also a little bit of memory and CPU power per node, so that you can at the end simulate a high number of nodes and their interactions. And the more abstract it is, the more scalable. But so, for example, you could have files which have a specific size that you send around in a simulator, but they do not have content. So that's, for example, where you save memory, or that you do not. So this is, for example, where you could abstract. So the content of the file is not really important; it's just relevant its size, for example. And next step is you can define a simulation setup. So what kind of node properties? So for example, bandwidth distribution and location and delay characteristics and all of this. And also define some actions that you can define various user models, what they should do. And you also define what you want to measure in this control environment in the simulator. It's helping you. Then you configure your algorithm, let it run, and see the results, so basically. And the simulation helps you then to calculate these actions and events and their interdependencies, and to retrieve the system properties, which are the quality of service or the response time and all these statistics. And it helps you also due to this statistics. So if you use the same metrics for similar kinds of algorithms, then you also can compare the results to each other. So for example, here these are the motivation, why is it needed in comparison to analytical models, is that you really, the constants and the resulting operation time really matters. So it's really important whether lookup time is below 1 second or below 3 seconds. And it's also relevant whether the costs are below 1 kilobytes per second or below 100. And also, so you really need the final numbers. What are simulations also used for? So you can also test do some parameter studies. So you vary the configuration of your algorithm, and you find out how it evolves, how it happens, what it leads to. You also use it to measure the system performance, so function times, cost, and all that, and also can investigate complex behavior. So how do these reactive behavioral strategies interact? For that, you can assume you have a set of strategies that the users might apply. So you have a good user, a selfish user, a malicious user, and then you see how do they interact and what kind of behavior emerges. Okay, so there are various types of simulations, and how a simulation can be run. So first of all, there are event. What is a simulation? So a simulated host is something that is depicted here in the graph. So every node has its current state. So for example, its current load, its current protocol state, and they interact, and it is managed through a simulating core that is providing some shared memory, and you have a set of actions that are triggered at every node or at individual nodes, and every node has its own protocol stack and interpreting the incoming messages and contacting other nodes. So very simple, but still you have to keep in mind every node has its own state. And you have two types basically of simulators. The first one is a round-based simulator, where you have, let's say, 10,000 nodes, and you cut the whole time in time slots. And in this time slot, you know which nodes want to do something. Then you calculate the effects, and the effects only take place from the next slot on, from the next round on. So round I only affects round I plus 1. So you do not have interactions in one round, and this is simplifying the behavior. It's easier to implement, and you can still see the emerging behavior of 10,000, 100,000 nodes over time. The second type is event-based simulations, where you have a timeline of events, and every event is scheduled for a specific time point. So also the same applies here, but with the round-based simulations, there's a large number of events sharing the same time slot, and here only one event takes place at one time. So, and every event might generate a new set of events. So for example, this is an event waking up node number 5, and it's the node number 5 receives a message. Node number 5 reacts on it and generates also some events. So for example, in 10 seconds I will do this and that, and I'm sending another message as a response, and the response message will be received in, let's say, 100 milliseconds. So every event might generate new events, and while going through the timeline, so every event is processed and one event is processed after another. So you see the differences. Here you have a strict order of events and only one event at one time, and here you have time slots where all the events internally take place at the same time and only affect the following events. So this is more complex to implement, but also more realistic, because every event can really influence every other event. So there are various simulators, and for peer-to-peer networks especially, and you really also need to have dedicated peer-to-peer simulators to simulate peer-to-peer networks. So just to tell you why, so there are also network simulators, for example, which are focusing on simulating the internet or routing in the internet, but they do not have this higher level for overlays and for creating new contacts with any kind of new nodes. There are also mobile network simulators, but the networks typically do not scale up to 10,000 nodes. That's more important, for example, that the MAC protocol is very correct. So with peer-to-peer simulators, the MAC protocol is not so relevant. Also the explicit internet routing protocol is not so relevant, but more the overlay. Okay, and there are various simulators. So for example, PeerSim. So this is from the conference IEEE Peer-to-Peer 09. There was a session on evaluation tools, and these are the popular ones. So PeerSim is very popular, and OverSim, that's also in Karlsruhe hosted, that rose as an extension to a mobile networking simulator. So it has a very strong network layer, so with WLAN correct implementation of the IEEE 802.11 standard, and so you have all these layers of underlay, then overlay, some massively multiplayer online game protocols, application layer multicast, and it's also able to communicate in a real network. And the last one, I think it's probably ended already, but it was very interesting, is so there you could create one real code and that you could simulate. So that didn't really use the benefit that if you have a controlled environment, you could save some memory, and so with this simulator you could only simulate up to 1,000 nodes. With the other two, starting with 10,000, it's a good number. I also want to some outdated ones, PlanetSim if it comes up to you once, or peer-to-peer sim. But there are not much more, so there are only these 5 plus the 6th one that I will present next. And it tells you just, it's a very hard task to really do a simulator, because it takes quite a lot of time to make it run and to provide it to the community. Still, I want to go into detail how simulations work and what should be considered while simulating peer-to-peer networks. And I want to show it with this simulator, pfxsim.com, that we are using. It started in Darmstadt with the in a project focusing on the quality of peer-to-peer systems. It was relevant to focus on peer-to-peer systems and various layers of it and their interdependencies. It's event-based, it's Java-based, up to 100,000 nodes, although realistically it's more 10,000. And the focus is on various layers, so not only overlays, not only the network, but also on, replication now or something else. So they're monitoring, and so it inherently supports that kind of various layers. And I want to just present you the layers just to make to show you what is relevant in evaluating a peer-to-peer network, what you should think of, what could have influence on the peer-to-peer protocol. For that, first, layered architecture. Okay, we have various layers. They allow to exchange the individual components. So you have, for example, 3 implementations for the network, 2 for the transport layer, TCP and UDP, several overlay layers. And for example, if you have monitoring that you want to host on Chord or on Pastry, you have dedicated interfaces so that you can see whether your monitoring is working on Chord as well as on Pastry, or whether there are some interdependencies. Okay, so I want to go into every layer to just show you what is relevant and what takes influence on this evaluation of peer-to-peer networks. And first of all, the underlay, the so-called underlay, which is modeling the network. So if you have, for example, your Chord network that you want to evaluate, then you do not really want to have the real internet, and you do not also want to have, so this is, for example, where Chord is running on, and this is Chord, but you still have the layers below, the transport layer and the network layer, which helps you to send and receive messages. And what, for your peer-to-peer application, you want to know is, if 2 nodes are communicating, what is the time that it takes for a message to pass? So is it 100 milliseconds? Is it 10? Is it 1 second? That, of course, takes influence on your lookup time, for example. Also, the bandwidth should be represented well. So if one host has 10 outgoing links with 1 megabyte each, then you want to make sure that its bandwidth is appropriately shared with all of those. And for that, you have these layers. And the main question is, most often, how long does it take for a message to pass? And there you could assume some simple network layer where you have, for example, static latency. Every message takes, between any nodes, 10 milliseconds. It's a very simple model. You could also have little bit variation there to say random between 10 and 20 milliseconds. You could also have distance-based latency. So if you know that the positions of all of the hosts, then you can somehow say, okay, this is the world, and it has it's a ball, and we have 40,000 kilometers in each direction. So we could say a message from Europe to China takes longer than within Europe. So we could make it distance-based. Packet loss can be omitted, and also packet size and bandwidth. So this is the simplest one. To make it more complex, one could use something like the global network positioning layer. And how is it done? So there have been some measurements in the internet, which basically Qaeda and MaxMind, and what they did is they took 100,000 nodes from all of over the world, and they should ping one specific position. So not one specific position, but let's say 100 or 200 specific landmark points. And to those, the distance was calculated. And what can be done? So basically, this layer helps you to choose a valid fragmenting and jitter and latency and all of these kind of models for your traffic. Of course, in all of those, the internet is not anymore visible, but only the statistics. So for example, if you have a latency model, then you do not send any more real messages around, but you just calculate what the latency would be. And also the same for packet loss. So there also you have packet loss based on statistics, based on measurements. and there you can use more advanced models from measurements in the internet, basically. And it helps you for your peer-to-peer overlay, for chord, for example, that you want to simulate, to really tell you if two nodes are communicating, what is the real correct packet loss and latency and jitter between the messages that are exchanged. Yeah. If you look at the overlays in pFactSim, but that's not limited to pFact. I mean, that's an overview for pFactSim, but there are also some for other simulators. So what typically is inside of these simulators, because it's a peer-to-peer simulator, is that you have a large number of overlays that are implemented. Typically, this is the main layer which grows over time. The service layer that we had, so for example, monitoring you can put in like PushSum or Snoop or SkyEye or some other management approach that you can put in for this control loop. So the idea is that between the overlay and the application you have some further services that support your application. And the applications you have like file sharing, for example, and user models like malicious nodes and good nodes. And what typically all of the simulators have is some integrated logging architecture. So as, for example, your overlay is generating some statistics. So every time a lookup is answered, you want to store the information. How long did it take? How many nodes had been contacted? And typically for that, you have some, you need some logging, like you want to find, you do not want to make the overlay itself calculating those statistics, but in pFactSim, for example, you have a so-called analyzer plane where you have classes that you can inform that something happened. You give the information and they do the evaluation. They create the statistics, they create the outputs, and it's quite convenient. Of course, you have also various churn levels somewhere available for your network, so that the CAD, that's an real-life implementation of Kademlia, and in that measurements have been done how long the nodes stay online. You also have some other churn models, so that is going into, and of course some visualization that helps you to see something. But typically, if you want to simulate 10,000 of nodes, then the visualization itself doesn't help you too much. So there you do not see anything. It only is nice to see for up to 50 nodes. And okay. What we wanted to do is, what it can be used for these simulations is, again, to pick up the topic with the monitoring, is that we want to see what are the effects and interferences of the configuration, for example, of the protocols. And you want to see what is the exact performance, for example, with monitoring. How many nodes do we really monitor? So this is the picture for the monitoring the peer capacities. And we want to make this capacity-based peer search, and our root node and its support peer have only limited capacity, so they cannot store the whole information of all nodes. But we want to see what's the ratio, how many nodes do they really see based on churn. So here nodes are joining, they are leaving a bit, and here leaving quite more. And what is the effect on the performance? So how does churn affect the performance? And this is really, really hard to model and to analyze. So here simulations help, and it tells you, so also if you monitor some sinus curve, how does the churn affect the monitoring? So here in this picture to the bottom right, we compare the tree-based monitoring with gossip-based and centralized, and you can all identify performance leaks and all this based on interference and with churn and with various number of network nodes and all this. So you can see what's the behavior under churn, how does it influence the topology and performance. And this is something that you cannot, or very, very hardly get out of analysis. And you also get a detailed view on, for example, the overall traffic and how do the various protocol aspects sum up the overall traffic. So for example, what is the ratio of lookup requests? So how much traffic is generated by lookup requests, how much traffic is generated by query answers, how much is traffic generated by the pinging of the nodes. So that all you find out. And overall, judgment on simulations is sometimes, okay, very nice now that you know that what the performance is and all that, but it's only simulated. And are your models really realistic? So is okay, here for example we found out, let's say, so under churn we have that amount of ratio of peers that we might observe. We find out some values, but they are all linked to the models that we use, based on the network model that we use, on the peer capacity model that we use. We do not have any attackers. We do not have very realistic heterogeneity. Do we really match all user behaviors? So these are some comments that are sometimes faced with simulation results. So you get some results, you have some performance results, but the question is always, are your models realistic? And one approach, okay, I'm not sure why this is there. There's probably a shifted slide. So what okay, that was with relation to the overlay and the applications. What you can also use it for is, first of all, of course, like file sharing that you can run on it. But if you have your overlays, you can also benchmark them. So that means the benchmark is sometimes known from graphical cards, gaming cards that are or Java servers or databases. And what you want to do is that if you have several implementations of the same interface, for example, so Chord is very similar in its functionality like Pastry and Kademlia. What you want to do is you want to compare the different systems with the same functional interface against the reference value or reference workload. And then you can say, tell some statements that Chord is 10% better than Kademlia due in this environment and all. Yes, and the goal is to, if you compare these solutions, to find a system which can deal best with the given workload. So for example, you can come up with the statement, Chord works best out of these three approaches in static environments, and Kademlia works best in mobile environments. And that's the one statement that you can do. And the second one is if benchmarking is also used to evaluate limits. So for example, in a database benchmark, for example, there you increase the number of requests and queries in the database until the database cannot answer them in a specific threshold or specific time. So you push the workload until the system breaks. That you could also do with peer-to-peer networks. For example, if you push the churn in which the nodes are joining and leaving the system and identify from which moment on does my system do not anymore perform correctly with lookups. That's also something to find out. Something more on benchmarking, because it's really a relevant aspect for the industry and the industrial usage of applications and protocols, is, so what do you have as an input? That's basically the big picture of benchmarking. What you have is you have a system under test, something like an overlay or various overlays. You have a benchmarking scenario which is holding it, and what you give as an input is a workload, so number of peers, number of requests per user, what is happening basically. What you want to pick out is the metrics, so load balancing factor, response time, traffic overhead, all this stuff. And the statements that you want to do as a final outcome is something based on the limits of the overlays, like overlay X is stable up to 50,000 peers and 10 requests per second, or a comparison of the systems that you tell, given a certain workload, so for example, we take the certified file sharing workload, and under this workload, Nutella is more stable than Quad. So these are the statements that you want to do. What are the challenges in benchmarking? So first of all, identifying correct workloads. So of course you can say we want to test the file sharing benchmark, but what does it mean? So you have to define what are the exact user actions, what are the exact node properties, what are the exact node network conditions. You also should justify it. So best if it would be based on some measurements that you really observed running file sharing application, that you know, okay, this workload is realistic. What you also want to have is to really have good models for the internet environment, for example. So network characteristics should be correct because they have a strong influence on the performance. And then it's the question, what do you really want to benchmark? Is it explicit interfaces, so for example the lookup interface in Chord, or is it something bigger? You also need to have the appropriate environment for it. So can you do it in simulations, or do you need something bigger in the testbed? How realistic should it be? And how do you, if you have that large scale system, how do you really induce the actions and measure the reactions? And yeah, of course, how to interpret the benchmarks, and what can you, how do you, how can you present the results? What is a result in a benchmark? Okay, some more words on benchmarking is if you pick your workload, what you want to do is basically, if you have various solutions, you want to pick the same workload for all of those. And there you have to define really a lot of parameters. So for example, how many nodes? So this is a snapshot for workload schemes for DHTs, for example. This is without churn, so the nodes join. Then you wait a bit, and here the actions start. So this is the stabilization period, and then the actions start. Or you have exponential churn. So exponential is referring to how long the nodes stay online and what's their online time. So they join, then you have a stabilization period, and then churn begins. You can also have massive leave or crash at a specific time, or massive join. So, and this is only to the number of nodes. The same applies for what kind of requests the nodes start, what kind of node users you have. If you have file sharing, for example, how big the files are, how the popularity of the files are, how the popularity of the lookups is distributed, so that all you can define and should define in your workload. Then you have to define the relevant metrics. So once you know what you put in, you have to know what you take out. So for example, you can define a long list of what you want to measure. For example, cost in the search overlay, number of hops to reach a destination, number of messages sent, number of traffic induced, number of, so the lookup time. There you can define a quite long list. And that allows you to really come up with some comparable quantification of something that might be referred to as quality. Okay, so talking about metrics, there are also two kinds of metrics. So first of all, there are so-called micrometrics. And the micrometrics. So let's start probably with the micrometrics. So they are more on a higher level. So there you can compare chord with pastry, for example. So the macrometric, let's start with the macrometric. So the macrometric tells you, okay, what's my response time, what's the freshness, what's the traffic that I'm generating for chord and for pastry. It's the same for both. If you find out, okay, pastry is performing worse, then you can look at the micrometric, which tells you for a specific overlay internally in pastry what the node count, what the routing time, what the average ratio for filling of the routing tables is. So these are overlay specific metrics that explain the macrometrics. Okay, and this is the big workflow of how benchmarking is done. So first of all, you need a scenario. For example, you pick the file sharing scenario. There you have to come up with, okay, applications. So file sharing is simpler. Then you need some valid models. So what is the file sharing scenario? What is the workload? You need to know what kind of the file sizes are distributed, how the popularity is distributed, how the number of nodes changes over the day and over the time. And that should be modeled so that you have exact workloads. So how your application, so how your file sharing application looks like, how the churn is, how do nodes go online and offline, what kind of users you have, what kind of additional services are provided. And the second one, you need the benchmarking description that tells you what kind of metrics you have, what kind of requirements you have. That's, for example, the requirement that from the files requested, if the file is available, so then it should be found in 99% of the cases. And that's also going to the workload generator. Then you take your simulator and put everything in that benchmarking platform and simulate it, or however you benchmark it. Okay, so this was the big picture to it, and one of the crucial aspects is really on also what should be also considered in simulations is how do I really obtain this correct model? So how do I measure the usage of Wikipedia or something else? And for that, so something that is really needed and that is provided is a so-called trace archive. So typically, there's not much knowledge about real peer-to-peer applications available because it's distributed. There's no central point to really measure at one point how many nodes they are, what kind of requests they are. And there's this trace archive which was presented in 2010, which helps to make available these traces. So what is a trace? A trace is basically a measurement over a long time of a peer-to-peer application. So what has been done is to place several sensor nodes or monitoring nodes which are observing the behavior of one application and measuring how many nodes are online, what kind of files are provided, for example. And it helps to really understand how peer-to-peer systems and file sharing applications operate, identify some weaknesses so that better solutions can come up to. So for example, there's a trace archive that introduced the trace format and provides some traces for BitTorrent, Gnutella, Skype, and PP Live, and it just helps you it gives you these measurements at hand that you can really use them as a workload. For example, to see, okay, what is the user behavior typically in Gnutella, or how do the lookups, the search queries, in which frequency are they generated, how do the nodes go online and offline, and this kind of information. Okay, I'm not sure. Okay, so talking about benchmarking, one example is a very general benchmark is in popular for peer-to-peer is let's benchmark chord in a file sharing environment. And for the benchmark, a very simplified workload is a typical file size between 0 and 10 megabytes. Requests and file popularity are CIF distributed. For the network, global network positioning has been used. The bandwidth is based on this international organization, which provide some statistics on the bandwidth availability in different countries. The metrics that are defined are this one, and I think we had this adaptive heterogeneous chord in the overlay lectures, so I just briefly show what was the difference. So this is the original chord. All of the nodes are similar. Most popular files are assigned by random, nodes are overloaded, and this was adaptive heterogeneous chord, where we had this additional layer where we ordered the nodes according to their capacities. And the goal was, if one node down here was overloaded, then it was picking an appropriate node on the higher overlay, which is able to be at a load. So you had the routing in the normal chord overlay. If that one was overloaded, then you had an additional hop to the node which was holding the file, and the file transfer was done from the strong peer to the requester. Okay. So, and if you want to benchmark it, then you have the same setup, the same workload, and the same metrics, and then you can compare, okay, we have, so the content itself is not relevant, but just that you can make the results comparable due to the same workload and the same metrics, and that is the purpose of benchmarking. Okay. Yeah, there you can check the duration to download the file, and then you can see how the lookup, the bandwidth in general was in kilobytes per second. And yeah, most of all, for this kind of benchmarking, simulations are used. And let's conclude with the simulations part. So the limitations of the analytical models were that although you have these general statements and you have you can say how in worst case your system performs and what in the complexities are, you're more interested in constants and what is the real performance of your protocol. And for that, simulations can be used. There you can typically simulate up to 10,000 nodes and see how what kind of performance emerges and what kind of behavior emerges with your protocol and with the various models. And the models are also somehow the weakness of the simulations. So they are used to, so they can be very heterogeneous, they can be very complex. There you have the network modeling and node modeling and capacity modeling. But the question is always, and based on these models, you induce some actions and the behavior, emerging behavior is analyzed, and you see so you can measure the behavior, which is hard to predict and to model with an analytical approach, and you see the interdependencies, and you also come up with these numbers on quality of service, like response time, traffic, and with what is really mattering. But the problem is that it's everything really also, first of all, the network is fake, the users are fake, and it's all modeled, and you do not know, are the models correct, are they good, or are they not good. So you get some statements on the quality of service, but the question is, so are these valid statements? So it's very much depending on the models. Okay, that concludes the simulations section. So let's continue with the next step, which is prototyping. So as it was said, the most important influencing factor in simulations are the models used. So what kind of network model, what kind of usage model, what kind of user model you have, and also you have the abstracted code. A step to improve this is to have real code, so to fully implement the protocol that you want to evaluate, and to still use a modeled user behavior, but at least if a running prototype, you could run in the internet, you have a real network with it and real code, and you get better results. Challenging in this case is, however, to coordinate the test. So if you have a large scale network in which you run your prototype, it's hard to coordinate, let's say, 10,000 nodes in the internet and to gather the results. Also, the coordination of actions and getting the results might interfere with the running of the protocol. So for example, if it's very important how much the bandwidth usage is influencing your prototypical protocol, and you use most of it for logging and coordination, that's disturbing the results. Just to give you two examples for such a prototype environment and testbed, that's Planet Lab. It's not 733 but over 1000. It has a full protocol stack, IP, TCP, UDP, application virtual users, and it's a global deployment, so around the world. What you get out of it is the behavior of your protocol under realistic network conditions like delay, jitter, or node load. Another aspect, another type where you can run your prototype is the EmuNet, which is EmuLab, and that means the motivation for it is, okay, let's simulations are abstracting from real implementation, so we take the real code, but we do not really want to run it in the internet. We still want to have a coordinated and controlled environment, so we have the network under our control. And this is a simulated network run in EmuLab. It's a software so-called, and it offers various network types like mobile networks and exact implementations of IEEE 802.11 VLAN networks. So you have the real code, but an emulated network, and also the users are emulated. But with that you can with EmuLab, multiple code instances could also be run on one single device, like a PC, and they communicate still over the emulated network. So although you have, for example, 10 instances of your software on one single PC, they still have the feeling that they are globally distributed on the world. Here's an example with two EmuLab nodes, node 1 and node 2, and the first and around in green are the peer-to-peer nodes, and they all communicate over this EmuLab nodes. And the first one is emulating a simulated wireless network with correct spread of the information and bandwidth and delay and all that. And the second node of EmuLab simulates the wired network like the internet. So you can arrange any kind of network constellations and let the nodes interoperate over this emulated network. So what's good for? So first of all, you have a real code and real pitfalls, so you really find the bugs in your code, in your real code, and you can use various network topologies and test your real code. You have still a observable and controlled environment. The drawback is the same with simulations. So how precise is the network? How valid is the network model? So is this simulated wireless network really well behaving like it is in real or not? Also, if you have various instances of the same protocol on the same on the same device, they all could use up the same bandwidth and interfere or CPU power. And if you have fake users, so only modeled user behavior, then you only have those kind of behavior that you modeled, but probably it's not realistic. Let's see how it can be done otherwise. So if you do not have an emulated network, but a real one, then you could start with a small-scale testbed network, for example, 37 PCs. That's, for example, the number that we had previously in the pool PC area that were available to us. And once we did this testbed-based small-scale evaluation with 10,000 seconds of testing time on 37 PCs, up to 500 peers, so instances. And what you can get out of it is to really identify the costs in a real deployment. So really how much traffic is used up. But it's less suitable for precision. So if you really want to find out the lookup times, the network that you apply it on is still modifying and influencing your results. So this is a pool PC from another university, just showing how you can run different instances of the same code on various machines. And what you could, for example, test is whether your code is really working under 10, 20 or 50% of churn, of leaving nodes, random churn. And if you pick up the example with the monitoring tree, then we used it here with an update interval of 5 seconds. And let's see what comes out.
Okay, so what we have is that with the testbed evaluation we can check the behavior under strong churn, and for example we also can measure the traffic over it very well. So this graph shows, for example, the applied net number of nodes. So first they joined and in very big numbers, and then we had 10% churn, 20% churn, random churn, and twice 50% churn. And we could observe how the network stabilizes afterwards. What we also could do, identify, is the real bandwidth consumption over in this small scale network. So it was around 3 kilobytes per second. And also we could just identify that how the protocol behaves under churn. That, for example, with the monitoring tree, the average calculation was not affected. What you can also find out is something more information on the structure of the tree, but that's not really relevant in general, but just tells you that you get a detailed information on the performance of your real code. Okay, if you want to extend the test bed, so for example have a large scale test bed, first of all, to clarify what's a test bed, that's a controlled environment of real computers on which you run your protocol. So the devices use real internet or intranet to communicate, and that also so you also have these faulty devices, slow network, device load, unexpected events that you do not really have in simulations and by far not in analysis. Planet Lab is a very prominent example. So there are 1077 nodes at 525 sites on the world. Here you see them in red dots. And you have heterogeneous hardware. They have strong and weak peers, different bandwidth, different delays, different load on the nodes. There's also a similar approach in Germany, where you have 153 nodes at 6 sites. Here you do not only have the opportunity to evaluate overlays like in Planet Lab, because in Planet Lab you cannot change the internet it's operating on. At the G-Lab you can also change the internet, basically. So the 6 sites are connected via cable, and you have the opportunity to also exchange the IP protocol used, the network protocol, the transport layer protocol, and you can test more networking layers than just the overlay. Okay, so what is the benefit? So first of all, you have real code, and you have real devices, and with that you also have somehow a validation of other evaluation results. The drawback is somehow Planet Lab, for example, is the biggest testbed available with 1077 nodes globally distributed. But that's not really a large number. So if you have a peer-to-peer network and assuming there are 1 million nodes, 1077 is not that big number. Also in G-Lab, for example, you have very powerful nodes, and they are long-living, not really adapting and applying the churn models. So that takes some impact. And in Planet Lab, it's very heterogeneous devices. That's good, but you have very high bandwidth nodes which basically do all of the work. All other nodes in Planet Lab, you just can assume that all of them have more than 20 programs running in parallel, consuming each other's bandwidth, and that's really difficult to make a statement then on the quality of your application. You also have one fake users, so you have to model the user behavior, and it is said that it's very time consuming to set up the Planet Lab evaluation and to do it, so it costs you 1 year, it is said. After having the test bed evaluation in a controlled environment, what you want to do is to have real users. So a real code, you have the full implementation of your protocol, real network with real delay and loss and jitter, and also real user behavior. But for alpha testing, you assume that they are friendly. So you have a closed user group of limited scale, let's say 100, that you know, that you ask to participate in your alpha test, and they also help you. They if you tell them to update their code, they do it, so they install the new version. If you ask them to perform some actions to test the functionality, they do it, and they are logging the bugs and feature requests and inconveniences, and the performance is logged automatically. So it helps you to identify still weaknesses in your protocol and to create a stable version. So how can this be done, for example? So you take PCs in a controlled environment, also additional PCs in the internet that belong to this closed user group, and typically you perform some functionality tests. So you ask the users to go through the whole functionality of the code and to test it, and to perform lookup, to perform search and all this. You have an integrated monitoring, and which tells you the current status of the network and how well it performs. And you ask the user at the end of the trial to answer you a few questions, how they liked it, for example, and what was most annoying, and how the quality of experience is. Let's assume you completed the closed user test. Next you have the beta test with public users. That can be very large. So just think of Google Mail, which was only released 1 or 2 years ago from the beta status, and YouTube as well. So you have up to starting from 1,000 users up to millions, and they are very picky and very hostile. So they are attacking also you cannot assume that they are friendly and helping you, and that they do not want to misuse the code. But it helps you to test finally the functionality and the performance of your protocol in a large scale. So you also there have logging, and to observe the behavior of the system, and that you identify additional drawbacks and leaks in your code, in your protocol, when the network is growing. So it helps you to create a final version to make it really publicly available and good. Okay, what are the challenges? So in order to create a large beta test with 1,000 users, you need a really attractive application so that users want to participate. And next, heterogeneity. So the devices are totally different. The usage pattern is varying a lot. You have attacking nodes, you have friendly nodes, you have selfish nodes, you have different kind of bandwidth. Everything you need to take into account. Also logging and monitoring. You might include it to monitor the performance of your approach, of your system, but it's also privacy risk for the users. So will they accept it or not? You cannot also control the usage anymore. So for example, if you have a file sharing application and you want to test how well it performs, then you have to expect that if one bug is found, people do not update their code, or you cannot ask them to perform any kind of usage patterns. And as I said, you might have malicious nodes attacking. So if you have a few nodes that are trying to attack the network, it might bring the whole network down. So you have to really think before how to counteract attacks. And latest, the misuse of your software, of your protocol. So if you, for example, have a file sharing application or social network based on peer-to-peer basis, and the people start storing child pornography in it. So how do you deal with it? So how can you prohibit and apply some access control and some privacy limiting censorship for illegal content? That's a very difficult aspect. But summarizing, testing is essential, so you have to identify weaknesses, verify the functionality, and also measure and observe the system behavior. You have to verify that your system works in a predicted and in an expected manner. Evaluation is part of the scientific work, so you have to anyway think of it. Evaluating distributed systems in comparison to centralized systems is very challenging, as effects only occur at a very large scale. So if you have a peer-to-peer network of 10 nodes, everything might work fine. So for example in Nutella. But if you have 1 million nodes, in not changing the code, it might break. Large-scale networks are very hard to operate and to control. So it's also so performing the tests are very complex. So summarizing, so evaluation approaches give you various tools at hand. So with analytical modeling, that really gives you good statements on the general case of, if you look at the graph, but often on the complexities that it derives. For example, chord performs in O log n, a lookup. It just means that you can find a constant C which is dominating. So C times log n is dominating your lookup time. But constant C might be very important. So it depends whether your lookup time is 1 second or 3 seconds, for example. So for that you have simulations, and there you can really find out what's the exact lookup time in a specific workload. But however, the problem is that everything depends on the models that you use. So if your models are not verified, the network models, the usage models, the application models, then the results are also not really useful. The final and the hardest part is the testing, to have a prototype, to have a test bed, to have real code, real users, real network. It's very hard to do in a large scale with more than 1,000 nodes, but we have to, because it's telling us most precisely how the protocol behaves.